Welcome to a new section. Today we are going to study electric field due to continuous charge distribution. For that, we need to understand what is continuous charge distribution. So, first we are going to study continuous charge distribution. We already studied in previous video that charge is quantized. That is one of the basic properties of electric charge. But the step size of charge, that is E, the charge of electron, is equal to 1.6 into 10 raised to minus 19 Coulomb is very small. So, even if we are considering a small measurement of charge, that is 1 microcoulomb, the number of electrons or base units in this 1 microcoulomb can be calculated as 6 into 10 raised to 12. We know we can calculate it as 1 microcoulomb divided by E, and that is equal to 1 microcoulomb is 1 into 10 raised to minus 6 divided by E. E we know it is 1.6 into 10 raised to minus 19. So, 1 microcoulomb divided by E is equal to 6 into 10 raised to 12. So, if we are considering a very small measurement of 1 microcoulomb, then that itself consists of 6 into 10 raised to 12 number of electrons. As a result, we can consider the charge is continuous in macroscopic measurement. So, we are neglecting quantization because it is impractical to consider discrete charges in macroscopic measurement. So, we are assume charge is distributed continuously. But remember, in microscopic level, we need to consider charge distribution as discontinuous because at this level they are discrete charges separated by intervening space where there is no charge. That is, charge is considered as discrete in microscopic measurements. That is, in macroscopic measurement, there is measurement of charge in a line, measurement of charge in a surface, or measurement of charge in a volume. We can consider the charge is continuous. That is, even if we are considering a small portion like this, in each case the number of charges or base units is very large. So, charge is assumed to be continuously placed. So, we can neglect quantization and consider charge is distributed continuously. If charge distribution is along a line, it is called a linear charge distribution, And if charge distribution is in a surface, it is called surface charge distribution. And if charge distribution is in a volume, it is called volume charge distribution. And corresponding charge densities are called line or linear charge density. We call it is lambda. Surface charge density we call it is sigma, and volume charge density we call it is rho. Now we are going to find the equation for the charge densities. First, for linear charge density. For that, we are considering a small element delta L and the charge is delta Q in that small element. Then linear charge density lambda is equal to delta Q by delta L. And for surface charge distribution, we are taking this small element as delta S, and the charge in that small element is delta Q. Then sigma is equal to delta Q divided by delta S. In the same way, we can take the small element here as delta V, and charge in that small element is delta Q. Then rho, the volume charge density, is equal to delta Q by delta V. In the reverse, we can take delta Q is equal to lambda into delta L, and here delta Q is equal to sigma into delta S, and for volume charge distribution delta Q is equal to rho delta V. That is, if we know the charge densities, then we can calculate or find the charge in that small element. So in linear charge density, charge in small element delta L is charge density lambda into delta L, and for surface charge distribution we can take it as sigma into delta S, and for volume charge distribution it is rho into delta V. If we consider this small element is very less, that is, when delta L tends to 0, this can be taken as dl. In this case, this can be considered as a differential equations. So we can take the small charge is dq, and that is equal to lambda dl. Or in this case, when delta S is very small, that is tends to 0, we can take it as ds, and we can write dq is equal to sigma ds. And for this case, we can take delta V tends to 0, then dv, therefore dq is equal to rho dv. So these are the equations we can study in terms of charge densities. So now we are going to study the units. We know the SI unit of charge density lambda is SI unit of charge per SI unit of length. So in this case we can write the unit as Coulomb per meter, and for surface charge density we can write it as Coulomb per meter square, because SI unit of surface area is meter square. Similarly, for volume charge density, the SI unit is Coulomb per meter cube. So we studied about continuous charge distribution. Now we are going to study electric field due to continuous charge distribution. If we know the charge in a small element dl is dq in linear charge distribution, then electric field at a point P, distance r away from that small element dl, can easily be found by considering this small element as a point charge. So in that case we can write it as dE, that is the electric field at a point P due to this small element dl is equal to 1 by 4 pi epsilon 0 into dq divided by r square into r cap. We know this we got from the equation for electric field at a point due to a point charge, where dq is the charge of that element which we considered as the point charge here. R is the distance from that point charge to the point P, and r cap is a unit vector in the direction from the charge element, that is the point charge we considered here, to P. If we know lambda, that is lambda is equal to dq by dl, or dq can be written as lambda dl, then this equation can be written as dE is equal to 1 by 4 pi epsilon 0 lambda dl divided by r square into r cap, where lambda is the linear charge density here. So what will be the net electric field at the point P? For that we need to find the electric field at the point P due to all elements and then sum it up. Or in integration we can say it is calculated by integrating the components of E under proper limits. So by integrating this equation under proper limits to get the electric field at point P due to the whole line or this linear charge distribution. In the same way we can write for surface charge distribution, dE is equal to 1 by 4 pi epsilon 0 dq by r square into r cap, and that is equal to 1 by 4 pi epsilon 0 sigma ds divided by r square into r cap. Integrating within limits, we can get the total electric field at point P due to this surface charge distribution, where sigma is the surface charge density. And for volume charge distribution, we can write 1 by 4 pi epsilon 0 rho dV divided by r square into r cap, where rho is the volume charge density. To find the total electric field, we need to integrate this dE component within the limits. If we are using the summation, we need to find the electric field due to each element here and then find the vector sum. So in general, we can write electric field at point P due to continuous charge distribution is equal to 1 by 4 pi epsilon 0 into integral within limits dq divided by r square into r cap, where dq is equal to lambda dl in a linear charge distribution, and it is equal to sigma ds in a surface charge distribution, and it is equal to rho dV in a volume charge distribution. In summation form, it can be written as E is equal to 1 by 4 pi epsilon 0 sum of all delta q into delta q divided by r square into r cap, where delta q is the charge in that small element, and we need to find the electric field due to each delta q for the whole linear charge distribution or surface charge distribution or volume charge distribution, and then find the vector sum, where delta q can be lambda delta L, sigma delta S, or rho delta V. You should remember here that r cap, r, and charge densities lambda, sigma, and rho all can vary from point to point. So we studied the technique to find the electric field due to continuous charge distribution. Thank you for watching this video. Keep learning. If you are not yet subscribed to our channel, please subscribe it. Also, please like and share this video.